see, we're good. All right. So what we're going to be doing, my friends, is going over load calculation. For load calculation, I have an example, guys. I'm going to go over an example of commercial office building. Very similar, not very similar, but similar, actually identical to the calculation that you guys did for the project. Identical. So we're going to be referring to articles. I might not write all the articles on the board because you guys have them. I gave you a copy of the Excel sheet, PDF, with all the articles that you need for the load calculation. Nothing new in the load calc. I just want to make sure that everybody knows how to do the calculation, the math in it. That's the first part of it. The second part, which I'm hoping I can do, is I can go over recreational vehicle and recreational vehicle park, as well as manufactured homes. How do you size a manufactured home park and a recreational vehicle park service? That's an interesting topic, right? And so these are the two, plus the commercial. And the last one I'm hoping is welding. If you have a welding shop, how do you size a service for a welding shop? And these are, guys, a special type of occupancy that needs special type of attention. Okay, so let's just go ahead. Here's what I have for this building. So please, these are given for this building. To help us with this, guys, I need you to go multitask, Mr. Irbab. So we're going to go to Article 220, which most of the calculation are in Article 220. Almost everything that you need is in Article 220. And to help me do this, I'm going to go have this example. Just a reminder, guys, this will be PDF for you and on the network. This will be PDF and put on the network. I do have a 50,000 square foot office building. You guys have an issue? Our building was 15. This one happened to be 50. This 50,000 square foot office building has a 300 fluorescent light. Each one of these lights is running at 1.65 amp. Now I want to bring to your attention two things, guys. I designed this building. So Brooks, I have the lights already in this building. We decided that these are the lights we're going to use. And we decided that we're going to throw 300. Who decided? The designer. We came up with 300 2x4 fluorescent lights like the one above your head. They're burning at 1.5 amp, 120. Okay? Given. These are given. You guys design it. Okay, so this one is given, designed. We put Brad on this project, and he loves receptacles, so he threw 500 receptacles in this building. Convenient receptacles, office receptacles everywhere, okay? Designed. I can't emphasize that. 300 fluorescent and the 500 are designed, already designed. Okay? So that's number 2. Number 3, I have a sign. By code, you have to have a sign, a 20 amp, 120 sign. I have only one of them. Number 4, I have heating and cooling. My heating is 15 kW 208 3-phase unit. And my cooling is 20 horsepower 208 3-phase unit. Okay, you can argue the cooling is small and the heating, but. And I have a pump that's doing some function. It's a 10 horsepower 208. I have a show window to show things, and it's a 40-foot show window. I have a track light of 100 feet and a kitchen equipment of water heater 5, dishwasher 2, range 10, and booster 3, water booster 3. Any question about the giving, guys? These are all information given to you. Information given to you by the designer. And then what the goal, Mr. Irbab, as we always have done in the past, is we need to go size a system, a service for this building. If you guys want to follow an example in the book, in this book, my code says 319, page 319. My code has 319. Very similar, identical, almost identical example. Any question about the given? Camille, my friend, any question? You have lights, receptacles, heating, cooling, pump, show window, and a few equipment in the kitchen. Any question about the given? I'll give you guys a few seconds to digest them. Okay, so all these things are given. Okay, all these are given, 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 and given, plus all this stuff. These are given. Anybody can guess?
What is that? That's 8 plus 8.
8 is kitchen equipment,
Okay.
water heater 5, dishwasher 2, range 10, booster 3. Come on, my friend. We just started. We waited for you guys. Just started, right? 2 minutes ago. Anybody can guess what the service should be on the system just by the loads, the type of loads. Is it 241.20? Anybody can guess?
124.
Yep, 28120. 28120. I'm not asking, but just by the loads, the type of the loads that we have, guys, you can kind of figure that this service is 28120. And of course, three phase. Like Spencer asked, when do I use 3-phase? You always use 3-phase if the 3-phase is available. That's the most efficient way of doing business. 3-phase. Okay, so what I'm going to do, guys, I'm going to go find the demand for every one of them, and at the bottom, I need to, what am I supposed to do? The goal is to size the service. That's basically my goal, is to size the service. Size the service for all these equipments. Any question, my friends? As I go, guys, through, I'm going to write the code articles. Please go to them and make sure that we know how to pick up stuff from them. I'm not worried about this if you don't follow me with the code for one reason, Ryan, because I already gave you the code and you guys did it for the commercial building. When I go to the recreational vehicle, we haven't done that. So please, I want you to go to the particular code and highlight it, as well as the welding shop. Okay, any question about the given? Any question about the given? This is what's given. Okay, what I'm going to do, guys, then, I'm going to follow step by step, 1, 2, 3, and do my calculation. I'm going to start by number 1. And what was number 1? Anybody remember?
Lights.
Lights. For lights, my friends, the NEC code book, I'm going to do 2 calculations for lights. A, the first one I'm going to do is A from NEC 2011, or doesn't have to be 2011. And the code, the article is 220.12. 220.12, it's a table. And from here, my friend, it will give me, if you don't know how to use this table, please do so. This, if you guys go to this table, what does the table tell you? The table will tell you 3.5 times the square foot of the building. 3.5 times the square of the building. 3.5 times the square foot of the building. And I'm not going to sweat it too hard because you guys are very familiar with that one. I'm going to go directly and put my 3.5 times the square foot of the building is 50K. And if you guys do the math on this boy, you're going to find 219 kVA. And please do the math behind me. I might have done the math wrong. Do the math behind me. So this is your demand for the lights. Your demand for the lights based on the code. Based on the code.
Where's that?
This is from table 220.12, Mr. Rabab.
I'm here, but where's the B?
3.5 office building. See that line that says office building?
You've got to take it times your
Times the square foot of the building.
slope to get the 219. Otherwise, that's not.
Yeah, so you take it, take that.
It becomes
Really, this
1.5.
175.
Oh, we didn't times it by 1.25. I'm sorry. Thank you. Times 1.25. And anybody knows why 1.25, guys? Anybody knows why 1.25? Continuous. Thank you. Times 1.25. Thank you. Actually, I have it on the paper, but I just didn't look at it. 1.25. So 3.5 from the code, 50 given, 1.25 continuous load. So this is A. B, and which we're going to choose the largest. B is actual. Actual is when we put Brooks on this project. Brooks decided to have 300 fixtures. Here's my 300 fixtures, Brooks. Each one of them you picked it at 1.65 amps. Here's 1.65 times, what's the voltage? 120 times 120 times 120 times 120. And because it's continuous load, we're going to multiply this by what? 1.25. Because it's continuous load, we're going to multiply it by 1.25. Let me repeat myself one more time. 300 is the number of fixtures designed by Brooks. 1.65 times 120, these are the amp volt for the fixtures that Brooks decided to use. 1.25, it's continuous load, so we multiply it by 1.25. If you do the math on this, one, you're going to end up with, if I did the math, and please check me, 74 kVA. 74 kVA. 74 kVA. Any question guys about that? 74 kVA? Anybody came up with, Brad, did you come up with something?
That's what I got.
74. 74 kVA. The last step, guys, is demand, lighting, demand. The lighting demand, guys, from table 220.42, lighting demand from table 220.42 is 100%. Lighting demand from table 220.42 is 100%. I don't need to derate anything, meaning I just don't need to derate anything. Okay, so write this one just so you can remember. And the last thing, my friend, is choose largest of A or B. Is that good English? Largest or larger? Okay, which one is larger for A or B? So the demand for this step would be what then? 219 kVA. And I'm going to put 2 stars next to it because that's a number I'm going to be carrying downstream. So this is the calculation for the lights. Only for the lights for this step, 219. General lights. When I say lights, can you add to this general? No task, no general lights, just general lights. So I picked the 219. Why did I pick the 219 over 74, Spencer? You take the largest.
The largest of what?
The largest of A or B, meaning step A or step B. Yep. Should it be the larger of A or B or largest? Doesn't matter. Yes, sir.
Yes. Anyway, I don't.
Go ahead.
You don't have to backtrack, but the 50K and then the 1.65, please. What's that?
50K is the square foot of the building,
Okay.
and 1.25. Which one?
1.2. Is that?
The 1.25.
The blue 1.65
Yes,
is the amps of the fluorescent light fixtures.
Okay.
Yeah, 1.65 is the actual load that Brooks decided to put in this building. I want you guys to pay attention to this number because we're going to carry it downstream to size the building. Any question about general lights? That's a general lights. That's my general light calculation. I put it all in one sheet for you. DJ, does it make sense?
Yeah.
Am I being recorded by you too?
Yeah.
Okay, good. Number 2. And I'm following step by step, guys. Hopefully that will keep us on track. 2. Receptacles. Receptacles. I'm going to do calculation for receptacles. If you guys remember, there are also 2 calculations for receptacles, Mr. Abdel. One based on actual and one based on cook. So let's go ahead and do the same thing. I'm going to use the NEC, and based on NEC, guys, I'm going to use 220.14K. And if you have not been there, you guys have been there. If you have not been there, please go there. It tells you 1 volt ampere square foot. 1 volt ampere square foot. So this will give me 1 multiplied by 5K, and that will give me a healthy 50 kVA. 50 kVA. That's directly from the NEC code book, only because it's office building or banks, office building. Mistake number one that I've seen over the years, Mr. Rabab, a lot of students take this one, Brad, and they derate it. So I want you to, just because I've seen it over the years, I want to write right here underneath it, no derating. So can you guys write, I want to write right here, no derating for A. Okay, can you guys write to yourself, very important, over the years, I've seen the students go and take this one and derate it. No derating. Can you guys, because no derating. No derating. Okay? So you just leave it as is. That's calculation number one. We're going to do two calculations, Ryan, and choose the largest. That's what we're going to do. Calculation number two, guys. Calculation number two is, or number B, calculation number B for the receptacle is the actual. I'm going to say this is actual. Everybody knows what actual, what Brooks decided to put in this building. What Brooks decided to put in this building, Spencer, you might ask about this one, 500. He put 500 receptacles. So I have a 500 receptacles multiplied by 180 from the code. Every receptacle has to have 180. And that will give me a healthy 90 kVA. 90 kVA. Please check the math with me if it's wrong. Okay, so that's actual. There's one little thing for actual. We need to derate. You have to derate the actual. So the step number two for actual, guys, is derate. I'm going to use derate here. Derate. And you're going to derate based on table 220.44. You're going to derate it based on table 220.44. This is how 220.44 says, guys. The first 10 kVA at 100%. Anything larger than 10 kVA, okay, we have larger than 10 kVA, so you take the 90 K minus 10 K and multiply this by what? 0.5. Larger than, and that will give you the 50%. Anything larger than, can everybody read this one, guys? Because that's confusion number one. A lot of people say, what are you writing here? This 90 minus 10 is larger than 10K. You cut it by half. Where do you find this? Right from 220.44. Right from 220.44. Mr. DJ, 220.44. Okay? All right, when you do the math, then add them up. Add them up. I'm going to put the plus here. Add these. Don't forget to add the 10. Mistake number two, Spencer. You people forget to add the 10 to the 50% of the larger than 10. If you guys added them up, and it should end up with 50, I believe. 50 kVA. Now you choose the largest of the two. Now you choose the largest. Did they come up with the same number? Good grief. Should have used it a little bit different. 50. And then the last step, I'll use in red, choose largest of A or B. Okay, which is,
Okay, why am I getting 40?
because you didn't add the 10,
Oh, cool.
right?
Yeah.
Yeah, if you add the 10, it becomes 50. Yeah, you took this, multiplied by 0.5, but you didn't add the 10, did you?
I did not.
Yeah, that's probably why you're getting 40. So you choose the largest of these two steps. They happen to be, guys, the same. So the demand for this step is 50 kVA. And please highlight it and please put these two little stars next to it, because that's what we're going to carry downstream. That's what we're going to carry downstream. Now, Camille, my friend, I want to bring to your attention, guys, if there was a multi-outlet assembly like in our project, the project that I showed you guys, If there was a multi-outlet assembly, you add the multi-outlet assembly to the 50 kVA calculation and you demand it. Had we have a multi-outlet assembly, you do the multi-outlet assembly, you add them here to the actual and you demand them. To the actual and you demand them. We don't have a multi-outlet assembly. But Mike Holt says in his book has multi-outlet assembly, so you multiply the if it's not simultaneous or simultaneous, 5 kVA, what is it, 180 for every 1 kVA if it's simultaneously used, or for 180 for every 5 feet if it's non-simultaneously used. But I can't emphasize, you're going to add them right in here and demand them. Okay, any questions about the receptacles? The receptacles. Straightforward receptacles. Okay, let's go to number 3. 3 says what? That's an easy sign. For the sign is I have 220 dot, and correct me if I'm wrong here, 220.14F, 220.14F, and from here, my friends, if you go there, it tells you it's continuous load 1.25, multiply by 1200, and that will get you a healthy 1.5 kVA. 1.5. I'm doing things in kVA. Mr. Rebab and everybody else in Jam, my friend, everybody knows when I did the math, I divided by 1,000 without putting it in the formula. I don't want somebody to say, well, how did you come up with 1.25? It's 1500 volt amp, Chad. My answer's in the K. When you get into the commercial guys, your answer's in the K. You have to be working Ks. A volt amp meaningless in a commercial building. A volt amp by itself in a kVA. So it's 1.5 K for the sine. I'm going to have close that one, and since I have room guys here, I'm going to put 4. 4, that's it for the sign, and I need to carry this number. Don't forget that you need to carry this number 1. So put that little star next to it. It's going to be carried all the way down to the sign. Number 4, I need heating slash cooling. Heating cooling system. I need a demand for the heating and cooling system. Let's start for the heating. My heating sounds very small, but put it anyway. It's a 15 kW. And since it's heat, guys, you can easily put 15 kVA and highlight this. 15 kW and 15 kVA, since it's heat resistive, the power factor is 1. The kVA and kW are meaningful, the same. Had it not been like this, you can't make the W equal volt amp. But it's heat. Okay, my friend. Let's do the cooling. A, B, cooling. For the cooling, guys, what do I have for cooling? For cooling, I have, how many horsepower do I have? I have 20 horsepower. I need to take it to table 430, 430.250. If you go at, what's the voltage? At 208 volt. At 208 volt. 59.4 amp. So motor, 20 horsepower, yep, 59.4. So then, if you do that, you're going to have 1.73 times 59.4 times 208. And if you guys do all this one, you're going to end up, if I did this one right, you're going to end up with a 21 kVA. 21 kVA. Please check that one too. 21 kVA. So I have a heating of 15 and a cooling of 21 kVA, non-simultaneous simultaneously use equipment. Simultaneously use equipment. Then you will use, I'm going to say demand. Demand, choose largest. And if you want to know where this says, I have 220.51 and also article 220.60. 220.60. That's where it tells you guys, especially 220.60. It will tell you to choose the largest of these two. So for this step then, what's the largest for this step? 21 kVA. So I pick the largest of the heating or the cooling, the heating and the cooling. Any question, guys, about how we calculated A? How we calculated B? 1.73 because three phase, Mr. Bab. If it wasn't three phase, you drop the 1.73, 208, 59.4, 21. Then demand from 250.51 to 220.60. Choose largest of, let's say, of A or B. Choose largest of A or B. Okay? So as we know, 21 is more than 15. Any question, my friends? My friend? Any question about the heating cooling? The heating cooling? No question for the heating cooling. What is 220.51? I can't remember 220.51. What does it say? Anybody 251?
Fixed electric space.
Yeah, fixed electric.
100% of the total connected load.
Yes. And that really, the 220.51 should be right here. 220.51. So you really, technically, you don't need it here. And cooling, for cooling, guys, you're going to go to Article 430 because it's a motor. Article 430. All Article 430. So that's how they should be in terms of code-wise. The demand, the 220.60, it tells you the demand, right, Brad? Did you look at that? 220, it tells you the demand. Because it's highly unlikely that you're going to have a chiller in a day like this in Minnesota running in your building. I told this one, guys, to a mechanical engineer, and they say they run certain loads, but not fully loaded. Tiny little, they might run 10% of a chiller in the winter or a heater in the summer for air exchange and so forth, but only 10%, 5 to 10% of a load. That's nothing. You can kind of ignore that. Any question about step number 4? I can't emphasize, guys, the importance of we do it here, and I already gave you guys an Excel sheet. Hopefully, with these two, it becomes stuck in your mind how to do load calculation. Can I move to the next step? Okay, step number 4. And by the way, you have noticed that my steps from the sheet that I gave you is different than these steps. There's no right way or wrong way of putting them in any order. They don't have to be in any order. That's the order that they're in right now is the order that I gave you the example. They could be, you could do the heat before the light, or the receptacle before the heat, or vice versa. Am I clear about this? Doesn't matter as long as you carry them at the end. That's what matters. Where at the end you carry them. Okay, let's go to number 5. What is number 5 based on the sheet that I gave you guys? Number 5, it says motors. Motors, and this is also Article 430. Article 430. Okay, for motors, Article 430.24 in particular, .24. Article 430.24. If you guys go to this boy, it will tell you I have a 10 horsepower. It's 10 horsepower. If you take this one to Article 430.250 table and under 208 volt, you're going to find that the full load current of that boy is what? 30.8. So I'm going to take 30.8 that's amps. Then you take 1.73, multiply it by 30.8. multiplied by 208. And if you guys do all this math, you're going to end up with, for motors, and I'm going to add 1.25 because it's a motor, one motor. I'm going to add 1.25 times 1.25. If you do all this, you're going to end up with 14 kVA. That's what you're going to carry downstream. Let me repeat myself here. We have only one motor. First of all, you need to go find the full load current of a motor. Then you need to multiply the motor by the voltage and its three-phase 1.732 if you want to put the 2. And then why did we multiply by this? Because it's only one motor, 1.25. If we have 5 motors, what do we do? We take the first 4, we do the calculation this one, and the last one, guys, we do the calculation for all of them without 1.25, and at the end, we add 25% of the largest motor. Which, Brad, in the big scheme of things, that 25 becomes meaningless. As you guys, if I have, like, when you have a MCC, and the MCC has like 50 motors. Adding 25 on the largest motor, at the big scheme of things, becomes really, as you're going to see later on when you have bigger systems, 25% becomes meaningless. But let's just leave it. Any question, guys, about step number 5? Since I have room, I want to go ahead and do step number 6 if you guys don't mind. Any question about step number 5? If you guys go to article 430.24, it tells you 1.25 times the full load current for a motor. Spencer, my friend, I always, in load calculation, always move with kVAs, always. So Holly's going to ask me, why didn't you add the amps, Chad, to the other amps and so forth? Don't you ever do load calculation based on amps, because a 30 amp 3-phase is completely different than a 30 amp 2 phases and completely different than a 30 amp 1 phase. Completely different. But if you put kVA, a 30 kVA 3-phase is the same as 30 kVA single phase is the same as 30 kVA 2-phase, guys. That's why we run with kVA, because if we're running with kVA, it doesn't matter if the load is single phase when you add them all up at the end. It doesn't matter if the load is 3-phase or single phase, as long as you capture it as kVA or volt amp. Everybody knows why I might have to multiply and convert everything to kVA, because kVA is voltage independent. I call it voltage independent. 30 kVA 3-phase is the same as 30 kVA single phase, the same as 30 kVA 2-phase. When I say the same as a load, when you will find the current is completely different, but as a load, it's the same chunk of power. It's like Spencer driving to school, or Spencer riding his helicopter to school, or Spencer riding a bus to school. The means are different. But it's the same kVA. I don't know if that's a good example, Spencer, but okay. Mr. Webb, did they hear something? Did they hear you saying something? Or?
No.
Okay, let's go to number 6 is show window, guys. I have a show window. I have a show window. For my show window, guys, I want you to go to 220.43. 220.43a, I believe. Can you guys check on that one?
Yes.
220. And it says for every foot, give how many?
200.
200. So that's where. So how many feet? Again, back to Brooks, because he designed the building. Brooks decided to have for show window. He designed his show window. When you measured it, there were 40 feet of it. So I have my 40 multiplied by 200. Everybody knows where the 200 came from. Multiplied by 1.25. All lights in a commercial building are considered continuous load. So the 40 is from Brooks designing the building. The 200 volt amp is from 220.43a, and the 1.25 because continuous load. Am I clear about this, guys? Okay. So if you do all this one for this step, it's a 10K. Am I right?
Yep.
It's a 10 kVA. and you're going to carry this one. You're going to carry this one, no derating. You're going to carry it all the way down. No derating, you're going to carry it all the way down. And because I'm going to be greedy, I'm going to stick another calculation here. So that's it. Show window. The feet multiplied by the 200 multiplied by 1.25, give you 10 kVA, add it all the way down. Add it all the way down. Eric, my friend? Ryan, any question, guys? Clear? No? DJ? No? Anything confusing? This is the feet that we designed the show window. This is from, this 200 is coming from 220 to 3A. And the 1.25, all lights in a commercial building is considered continuous load. Number 7, guys, since we're at light, track light. And some of you ask me, what's the difference between that track light and a show window? If you put the track lights in a show window, becomes a show window. If you put the track lights right in here, which is not a show window, becomes a track light. Really, nothing. But you don't have to put a track light in a show window. You can put any type of light. So track lights, for track lights, my friend, lights, and this is coming from the 220.43B. 220.43 and a B as in boy. Track light, it says for every 2 feet, you give them, every 2 feet, you give 150 volts. Okay? So how are we going to do the math? How many feet did Spencer design for this building? 100. So here's my 100 feet, divided by 2, and multiplied by 150. And I don't know about you guys. Here's 100 feet, divide by 2 becomes every 2 feet, multiplied by 150. You can do it any way, shape, or form. You can divide the 100 by 2, it becomes 50 multiplied by 150. Any way, shape, or form. And then don't forget, because it's continuous load, what do you do with it? Sorry. You multiply this all by 1.25. And if you go all this one for 7, you're going to end up with 9. 9 kVA. Brad, anything wrong? I see you laughing.
I just think it's funny that they say it's 150 for 2 feet instead of saying 75
Yeah.
per foot.
Write a proposal. It really is. That's what I said, guys. It's really, it's a good way of making it easier, because people who write the code have been doing it, guys, for years. They don't see. The bad thing about doing the same thing over and over, you don't see it differently. Somebody like you coming and looking at it from different way, I think has a fresh way. Write them a proposal. We do. Now, Mr. Erbab, we divide by 2 because every 2 feet. We multiply by 150 because the code says so. Everybody knows that, guys? We multiply by 1.25 DJ because continuous load.
Yeah, I know that.
I'm just, why are you happy? You're getting happy up around the edges. What's going on with you? I thought we were friends, man.
We are. We don't put that on sheet.
Okay. Any question, guys, before I move to number 8 and the last one? Number 8. And again, an identical example, Spencer, is in my code book. Almost identical. I mean, it's not really rocket science. Kitchen equipment. Kitchen equipment in a commercial building. So please, we're going to go to 2. For this one, you need 220.56 and also table 220.56. You need the article and the table to understand what we're doing here. The article and the table. If you guys read the article and the table, here's the equipment that, who did we say, Brooks did the design. Brooks had in this building a water heater, and his water heater decided to put it at 5K for this building. And dishwasher, this is just for domestic hot water. Dishwasher, so you can 2K, and range, so you can bake pie and all this good stuff at 10K, and booster at 3K. All these are equipment, kitchen related equipment. all these are volt amp, volt amp, volt amp, volt amp, volt amp. If you add them all up, guys, you're gonna end up with a 20 kVA, and then apply demand from table 220.56. How many of them do I have?
4,
I have 4. What's the rate? What's the demand factor for 4 equipments?
80%.
80%. So then you take the 0.8 times 20, and if I remember these days, right, that will give me 16 kVA. And this is the number that I'm going to carry. Anything that has a star, guys, I'm going to carry it all the way down. Any question about kitchen equipment? For commercial kitchen equipment, add them all up, apply demand factor. And please read the 220.56, commercial kitchen equipment, not residential. Remember how we did the whole calculation for residential demand for, had this been residential, we'll do it completely different. The ranger with the range, the dryer has their own, and the water heater has its own, and so forth. Done. Now, if you have other loads, Jim, you just keep adding step number 9, number 10, number 11, keep going with them. We don't have it. So the last thing, any question, Mr. Rebel? Can I go to the next step, Mr. Rebel? No? Just a reminder, this is captured as a PDF file too. The last step, guys, which is, this is where we're going to do size, service, equipment. Okay, I need to size service equipment. All what we're doing is just to size service equipment. This is how we're going to do it then. I'm going to just list them, guys. Light, for the lights, what was the demand for the lights? 219 kVA. Number 2, this is a different color. Number 2, red, receptacle. The demand for the receptacle was 50 kVA. And I'm just copying. Number 3, copying what we did, guys. Sine. The sine was 1.5 kVA. Number 4 is heat cool. Heating / cooling. And what was the demand in this one? 21 kVA. And motor, number 5, motor. You don't have to do what I'm doing, guys. I'm just summarizing them. Motors, I have 14 kVA. And show window, number 6. Show window. For a show window, I have 10K. And track light, number 7. Track light. Track L. Track light. Track light. For track light, I have 9K. And the last thing is number 8. I have it for kitchen. Kitchen equipment, and I 16K. 16 kVA. And well, guess what we're going to be doing for all these? We're going to add them up. That should come up with 341, Brad. Did you come up with something like that? 341 kVA. That will size the service. Now let me, as long as we're here, guys, let me just bring to your attention a few things. This is just sizing. I know my service needs 341 kVA. That's what I need. By the way, you can go size a transformer based on this now. If I ask you to go find a transformer, your transformer has to be 341 kVA or higher. It's not standard. You go next higher. Okay, so we know how to size the service. If I ask you guys to size the lighting panel, if you want to size the lighting panel, okay, let's see what's light. If I want to size the lighting panel only, you go to step number 1. Here's light. You know what? Let's do the panel. We'll get back to it. Any question about adding them all up? I'll get back to the panels, other panels, if we're going to size other panels. Any question, guys, about this? 341 kVA. As I said, guys, we always move in kVAs because kVAs is not dependent on the voltage. kVA is not dependent on the voltage. Thank you. kVA is not dependent on the voltage. Okay, now you're going to ask me now what type of voltage system, Chad, you want. We were working with 28120, so might as well continue 28120. But by the way, at this point, you can change your mind and make the system 48277. But guess what? You need the transformers then downstream. It makes sense to continue with 28120. I'm going to write my equipment here just to remind us that this is a 208/120 three-phase system. Just if we forgot, 28120 three-phase system. Three-phase system. Just a reminder so we don't forget. It could be any system. Spencer, this calculation could be for any system and it works. Any system, any voltage system, single phase or three phase. Okay. Sorry, did I go too fast? No? Good. Okay. Now let's do the following. Since you guys are big boys, grab ugly, and we're going to size the following from ugly, not ugly, DeWalt. We're going to size the following. First, the panel. First, we're going to size the panel. So I need to sizing service. For number one for sizing is panel size. Panel size. Okay, for panel size, guys, for panel size, I'm going to go for all of them, as a matter of fact. I'm going to find the I. First, you need to find the I. I equal kVA divided by 1.73 times the voltage. Don't you ever forget this formula. So what was the kVA for me, guys? 341 divided by 1.73 times 208. And don't forget there is a K. I have 948 volt. Volt. What am I talking about? And now I'm talking amps. When it comes to sizing the panels and sizing the conductors and sizing panels and conductors, guys, we're talking amps. Okay. Now I want to go to DeWalt, size the panel. Remember, that's just the cover inside the panel. I want to take this amp to size it, the panel size. I want to take you guys to DeWalt. TW is what? DeWalt. DeWalt from now on. And page, you should be able to go to, where's my panels? 312. 3-12. And remember, it's a three-phase, guys. Size of it's a panel board, three-phase. I can't fit it in up to 600, so I have to move to where? I have to move to switch gears. I can't find it in size of a panel board. I exceeded the panel board, so I'm going to move to actually 313 in this case because of the size. So this will be 3-13. It's not a good 3. All right, let's go one more time. 3-13. Everybody knows what 3-13 DeWalt? If you guys go to switchboards or switch gears, what's my next standard? Three-phase. Look at the three-phase section. Do I have 1,000? Do I have 1,000? 1,200. Now I want to warn you. This is, guys, the cover inside the panel, not the overconduction device. The cover inside the panel. So my panel. Why this will help you, Spencer? Because now you can go by. When you estimate it, you know that your panel have to have enough cover for 1,200 amps. So this has to be a 1,200 amp panel. And everybody knows what the voltage is, of course. It's 28120. 1,200 amp panel. We size the panel. I probably should come up with, here's my panel. So this size is for a 1,200 amp. This is for the cover right here. The cover size, okay? The cover size 1,200 amp inside it. Now, the next thing, AB, the thing that I want is over current protection device. That's the fuse ahead of it. Over current protection device, guys. I'm going to call this one, just to get you an idea where we are. This is A, this is B. I want to size the over current protection device, B. What do you guys think the over current protection device should be? 948 amps. This one is going to go to NEC 240.6. We all know that, right? Or from DWALT, you can get it. What's the next standard overcome protection device? That's where the 1,000. Somebody said 1,000? That's where the 1,000, guys. The next standard overcome protection device is what? 1,000 amp.
It's over 800 amps, so you can't go up with over 800 amps.
You can. Now you can size the conductors to match the overcome protection device. Yeah. You can't if you want to. I think you're confused, but 800 amps you can, for up to 800 amps, your conductors can carry the load, but the overcome protection device can be slightly higher than the conductor amps. But if your conductors, if your load is higher than 800 amp, no problem. You just match the conductors to the overcome protection device, and that's what we're going to be doing in a second here. Any question here? So everybody knows where the 1,000 amp now. Oops. I can't emphasize this one, guys. There's a B here, and what is this? 1,000 amp. Now, Holly, you're absolutely right. From a code point of view, Ryan, my friend, this is a 1,000 amp panel. From a code point of view, it is a 1,000 amp panel because the code says, guys, the amp of the panel goes by the amp of the overcome protection device. This panel could be a 400 amp panel, cover-wise. If I put a 200 amp ahead of it, it becomes a 200 amp panel. Okay? I want to distinguish, guys, between the cover size, which most of the time in the code-wise is meaningless, but it's good for you as an estimator because that's what you're going to be buying.
What code is that says that you have to match it like over 800?
The 240.4.
4.4.
240.4.
240.4.
Yep. Okay. Any question, guys, about these two values? Now, for all practical reasons, your panel is actually a 1,000 amp panel. It is a 1,000 amp panel. The cover in it is 1,200 amp, but it is a 1,000 amp panel in terms of service and everything else. Okay? Then, so we have the overcome protection device. The last one, guys, is A, B, C, service, entrance, conductors. Can you give me that one again? 240.4. 240.4. If 240.4, guys, if you go to 240.4, it says if it's higher than 800 amp, which is we are, then you have to match the overcome protection device. 240.4. Let me just go to 2. You don't need to know that one, but if 240.4, Chad. 240.6 should be 240. Protection of overcome protection device. B and C. In this case, it's a C. And a C. Yeah, 240.4C. Very important, guys. Overcome protection device over 100, where the overcome protection device is rated over 100, the ambiguity of the conductor it protects shall be equal to or greater than the rating of the overcome protection device. Everybody see that? Please highlight that one. If the overcome protection device is over 800, which we are, then the amps have to match the overcome protection device or be higher. Can you guys write yourself? Now, if we were less, then you go to C, to B, which is you can size one overcome protection device higher than the ambiguity of the conductor. Okay, based on this, guys, then do I need the question, Spencer? The question is, should I use the 940 amp to size, or should I use the 1,000 amp? 1,000 amp because of 240.4C. We're higher than 800 amp. Everybody understand this one, guys? If we were lower than 800 amp, then I can use that number. Say this was 748, right? Say this number was 748. then I can use the 748 to size a conductor. Okay? All right, so in this case, based on 240.46, and then match, I'm going to say here, match, there's a T, match over current protection device. So what does that mean? Means I have 1000 amp, and I want to size a conductor for this. I don't know about you guys. When you size it, I'm gonna run. I can't size one conductor, so I'm gonna run. How many runs do you guys want? Should we do 3 runs, 2 runs, 4 runs? Give me a number. 3 runs. Let's divide by 3. So that will give me what? 3.3 amps. Take this one to NEC 2011 310.15 B16. Disclaimer, this is 2011. 310.15 B16, which is 310.16. And what's the size of a conductor that can carry 33.3 amps?
400.
400. How many conductors?
Let's say for 3.
Okay, I will run full neutral. Let's do the phase, guys. Let's just do the phase now. It's a 3-phase, so I need 3 conductors. Each one of them is 400. Each one of them 400 kcm. 400 kcm. Okay? You can, yep. Which page is that? 344, yep. 344. Here's how I do between DeWalt and the NEC code book is if the information is in the NEC code book, I always refer to the NEC code book. If it's not in the NEC code book, I always refer to DeWalt. Everybody knows how interface with me from now on. Because it's good because if you go, Jim, the reason behind this, if you go to the inspector and see DeWalt book says that, I don't know what book are you talking about, you know what I mean? So I refer to DeWalt only if the information is not in NEC code book, at least in the examples. Any question, my friends? Any question? Okay, here's what I'm going to do. Do you guys need 5 minutes break? Here's what I'm going to do. I'm going to do 3 things. Actually, yeah, 3 things. Number 1, I'm going to size the neutral. Number 2, I'm going to do the bonding and grounding for this system. And number 3, I'm going to show you how to size other panels. We're not just like, what if it was a lighting panel? How would we do a lighting panel? Then we're done. So you guys have 5 minutes? You guys have 5 minutes, quick? And then we'll do that. I'm sorry, 341, Mr. Rivera?
That's the total of
All the KVA, yep. This is, I should have put K here, because otherwise it will be confusing. 300K, 341K. All right. Okay. 2 things, guys. Let me go back. So we sized 400 kcm. It's recording. Thank you. I'm gonna go and size my neutral. The only reason I want to derate my neutral because of very important concept, because I have 4,000 amp panel. Otherwise, it's not worth it to go and look at the neutral. It's really not worth it. Okay. Let's go look, guys, at the whole load. Everything in the whole load and see which one is going to carry. Go to step number 1 with me. I want you to highlight things that are going to carry as a neutral. Things as we're going to carry as a neutral. So I'm going to go to these steps. Just highlight the things I want to carry as a neutral. Only the stuff that's going to carry as a neutral. Lights. Now for lights, I know you're going to ask me, Holly, you're going to say, Chad, this is harmonic lights. We're not going to derate them and all this good stuff. The reason why I want to do the lights, guys, is because 1000 amp or more, and I'm looking at the big picture. So I'm going to put my lights in and derate my lights. That's the only reason. So do you guys agree with me that all these lights will be running 120 to ground, right? 120. So all this, the lights are going to be carried. So what I'm going to do, I'm going to put a green in my way. Anything I'm going to put green next to it means it's going to be carried. And I'm going to put neutral and next to it. Means this number is going to be carried downstream as a neutral. Yes, sir.
So if we're running it on 277, it would still
Absolutely. It will be neutral. If your lights are 277, it will be neutral. Yep, absolutely. Anything that running 120 or 277 is going to be neutral. Okay, so that I just put just 2 stars, different color, and put N next to it. Means it's going to be carried downstream. That's all what you need to do. Let's go to the receptacle. Do you guys agree with me that 50K are 120 neutral loads? So what I'm going to do next to the 50K, I'm going to put a star next to it, and I put N. I'm going to highlight it. N for me is what? Neutral. So this is going to be also carried as a neutral. This is going to be also carried as a neutral. Okay, let's go to the sign. What do you guys think of the sign? Sign is 120, so nah, Chad, it's going to be a neutral. It's my neutral. N. I'm just going to highlight it and put N next to it. Heating, cooling. Now that's neat thinking. Are my heating, cooling 3-phase or single-phase? 3-phase. Do I need to carry anything from this junk here? Why? No. Why? All these 50 kVA, I assume it should be all 3-phase. This step, guys, is all 3-phase balanced. Do I need to worry about it? No. So I'm going to write myself no neutral load here. No neutral load. Okay? I just wrote myself a note here. No neutral load for this step number 4. Because why? Everybody knows why? Brooks, 3-phase, right? Because 3-phase system. It's balanced. Okay, so no carrying. I'm not carrying. What does that mean? I'm not carrying the 21 kVA down. All right, let's go to the motors. Is the motor 3-phase that we have? Do I need to worry about neutral here? The same thing. No neutral load here. No neutral load. And if you guys, I'm going to write it here. And why? 3-phase balanced. And if anybody wants to know why, it's a 3-phase balanced. Okay? 3-phase balanced. I don't have neutral. I have the luxury of having different color than you guys, so it's easy. Again, all this will be PDF'd, colored for you. So that's really, and recorded. So, window. Do you guys agree that that 200 volt amp is going to be most likely, unlikely it's going to be 3-phase. It's going to be 120. So this load here, I'm going to put my stars next to it, green stars, and I'm going to put my N here. What does that mean? Carry it downstream, Chad. Yeah. The same thing for track. The same thing for the track. I'm going to put my green stars next to it, and I'm going to put N here. What does that mean? Carry it downstream. Are you guys following me? I'm just picking the loads that apply to neutral loads that will contribute to the size of a neutral. The motors and the HVAC cooling, I threw them out because they were 3-phase system balanced. Had this panel been 400 amp, I wouldn't even mess with it. Full neutral. Oops. Oops. Let me put my. All right. Next, kitchen equipment. You guys agree with me? These are 120, right? So I'm going to go here, star my green star, and I'm going to put my neutral next to each one of them. I carried my neutral. Anything else left? So the kitchen equipment is going to be neutral. Had been a 3, had been the range 208 120. These most likely they're 208 120 ranges. You're absolutely right. Most likely it's going to be a 208 120 range. But again, had you have a 3-phase range, this is the good question. Have you had a 3-phase range? I would pull the 3-phase range out of the equation and do it. My assumption is going to be this is a 208 120 range. Can I write this one, guys? The range was a big boy. And the water heater, this is going to be a 208 most likely volt. And this one is going to be a 208/120 volt. And if it's a 208, would it contribute to the neutral, guys? It would, because it's unbalanced system. The system is unbalanced. You need 3-phase. These are 3-phase system. The only balanced load is going to be is what? Is the 3-phase. Okay, so that's my assumption. So I carry the neutral because of them. If your assumption is different, you grab certain loads and throw them out the window. Okay, come on, soak. All right, let's go then. Oops, did I get the kitchen? All right, now I'm going to come over here, guys, and I'm just going to add the loads, only the loads that I need, and I'm going to write them in green. So I need 21 K, right? I have 50 K, right? 1.5 K, heating and cooling, 0 K, motors, 0 K, show window, 10 K, and 9 K, and 16 K. Can you guys give me the adding? This is for neutral. This is for the neutral.
The light on top,
Did I forget something?
It's
Yeah.
219.
219. You have 21 on
first one. the light.
219, thank you. This is 219. 219K, thanks. Okay, can you guys add everything and give me the answer here? Neutral load. Sorry? Anybody come up with it? Brad?
290.
I can't hear you guys. 290? 290.
No, wait.
306. Yeah, I guess
Pull off the
306.
heating and the motors, right?
Yep.
306.
So that's 35 minus 41, 306.
So I got 206.
How much?
306.
306. You guys have to make up your minds here.
I did too.
306. 306, okay?
Why are you guys at 16?
Get your code, man.
Did we decide that it's 3 phase?
Yeah.
Or just, okay.
We decided it's going to be non-three phase. Okay? So 306. Any question, guys? So that's my neutral load. Again, you have to look at anything three phase, grab it, throw it out the window. All right. So I decided that these are 306. Then for my neutral, I'm going to go all the way, guys. I skipped this step and go to A, B, and C here. I'm going to go to C. C, neutral size. Okay, what was 308? What is 306? And I'm going to size it for 306 kVA. Okay, so I have 306 divided by I. I need to find I neutral, guys. Divided by 1.73 times 208. And that will blow your mind. Say, why are you dividing it by three phases? Because it's going to be balanced between the three phases. If this goes in one phase, you're doomed. It's going to be balanced by the three phases. Yes, it's a neutral load, but it's going to be balanced by the three phases. K. So 306 kVA. 306 K. Okay. Anybody has a calculator handy? I did not do the 850. 850 amp. 850 amp. Right?
Yep.
Anybody come up with something different? Okay, 850. 850. So 850. 1 second, yeah, we have another thing yet. We know apply. Okay, dwelling units. Neutral conductor unbalanced shall not be applied to the okay three phase ground and conductor. Okay, neutral conductor. Okay. Okay. Neutral conductor. Adjustment factors. I just want to find one thing here, guys. Give me a second here. I don't have it 220. The neutral. What is it? 220.60, I believe, the neutral, right? 220.60. Yeah.
That's 61.
Yeah, the 61, that's all. Okay, for 2, I'm just going to put 220 now. Up to this point, guys, I need to go to 2 and EC
20.
220.60, 220.61. I'm going to go to 220.61, and it will tell you, if you guys read 220.61, really interesting, it will tell you can derate if you 220 in particular a portion of unbalanced excess of 200, especially 220.61b2, 220.61b and 2 in particular. If you guys go read that one, it tells you if your neutral is higher than 200, cut anything higher than 200 by 70%. If you're neutral higher than 200, cut anything higher than 200 by what? 70% again. That applies for everybody. All right, so let's go and see what's the deal. Based on this, please go to this one. So I'm going to take my 850 amp. The first 200, what do you do with them? Leave them alone. So the remainder is 850 minus 200. You're going to slam these by what? 0.7. And what do you need to do? Add them up. I can't emphasize. Where did I come up with all this mess here? From 220.61b2. Anything higher than 200, cut it again. You don't want you guys to carry cover and throw cover in the ground. That's not doing anything. It really is. Neutral is not doing anything in a three-phase system. Bigger systems. Okay, I did not do this math, so I need somebody to do the math for me.
Yeah,
All together,
Yeah.
655. Yes.
That's right.
655 amp. 655 amp. Okay? 655 amp. So, does that make sense? I can also cut 70% of anything higher than 200, so I cut it. Then I'm going to parallel 3. Now remember, do I have option to parallel 2 now, or I already parallel 3, so I have to parallel 3. So I'm going to take my sizing neutral conductor. Okay, I have my 655 amp divided by 3. Why do I have to divide by 3? Because I size the phases for 3. So that will give me 200 something.
218.
218 amp. Take this one to 310.15b16 under which column? 75-degree column. I hope you didn't forget that 75-degree column. What? We have one conductor for aught. One conductor for aught. One conductor for aught.
Yeah, then we're gonna run into a problem with the grounding. Right? So we have to go up.
With a grounding electrode conductor. Yes. We'll check that one later. Any questions about the 4-aught? So far, we have our sizes 4-aught. So let's put the things, all things considered together. I have my panel. Mr. Rebab, I'm not going to go back. Oh, sorry. Sorry for that. So I divided 4-aught. By the way, if you end up with number 1 here, what do you need to do? You can't parallel less than 1-aught. You cannot parallel less than 1-aught. If you end up with number 1 here, you have to go to 1-aught anyway because you're paralleling. That's catch 21.
I'm okay, sir.
Thank you, Mr. Beb.
Yep.
Okay, so let me go, guys, back to the system, my system. Here's my overcomputation device, 1000 amp, 1200 amp. Here's my ground. Here's my neutral. I need to size the following, guys. I need to size the bonding jumper, since you guys are bonding jumper. And I need to size the grounding electrode conductor. Earth. So I'm going to call this one number 1, and I'm going to call this one 2. Okay, I'm sizing grounding and bonding now. And I want you the title here, grounding slash bonding for the system for service equipment. I need to size, now we size the phase and the neutral. We need to size the grounding and bonding. It's part of your job, right? Grounding and bonding. We're going to size the grounding and bonding. I want you guys to know how many sets do we carry here. We have 3 sets of 3 conductors. Each one of them was, what was it? 400? 400 kcm. 3 sets of 3 conductor, 400 kcm. I'm not looking at the neutral now. And I need to size the grounding and bonding. Okay, so any question is, I need to size the grounding electrode conductor and the bonding. So I need to go to, in a case like this, we need to, number 1, let's say number 1. Number 1 is grounding electrode conductor. Grounding electrode conductor. We need to size this boy. And where do we go for this boy? 250.66. Here's what the code says, guys. I have 3 sets. Multiply the 3 sets by what's each one of these phase sets. 400 kcm. That will give me what? 1200 kcm. Take it all the way to table 250.66. What's the largest conductor that can, from under cover, under CU cover, what's the largest conductor I can size?
You're larger than 11.
If you're for grounding electrode conductor, if you're larger than 11, you stay there. For grounding electrode conductor, don't do anything. What's the largest? 3 aught? Was it 2 aught or 3 aught?
Oh, good.
3 aught. So the size is going to be 3 aught copper. So this conductor is going to be 3 aught. This conductor is going to be 3 aught. Any question, guys? This conductor is going to be 3 aught. Let me just make room here for my stuff. This is 3 aught. Always cover unless you hear otherwise. Okay, so from this table you can come up with 3 aught. Any question about the 3 aught?
Yeah, why
Yes,
wouldn't
sir.
we use the 1000 amps instead of 1200?
Because if you read 250.66, it tells you you size it based on the conductors, not the overconduction device. The article, if we read the article 250.66, it says size the grounding electrode conductor based on the conductors coming to the building.
Which we decided the service entrance conductors was 1000 amps divided by 3.
Yeah.
So our total is 1000, not 11.
Yeah, but we size them based on the cover, the KCM, not the amp. The KCM, not the amp. If there was an equipment grounding conductor, Brad, you're absolutely right. Equipment grounding conductor based on the amps. Any question, guys? We size the grounding. Remember what I'm talking about? Grounding electrode conductor, not equipment grounding conductor. The last one here, guys, is number 2. Number 2 is the bonding jumper. As you know, in an NEC code book, 3-phase or single-phase system, you have to take the ground and the neutral, bond them together. For safety, consistency in the neutral voltage, always 120 or close to 120. Okay, so now that's called system or main bonding jumper. Main bonding jumper. Main bonding jumper. $250.26. 28. Yep, 228. Main bonding jumper. 250.28. 250.28, and also table 250.26. 250.66. If you guys go to table 250.28 and 250.66 table, here's how it tells you to do it. You do the same calculation. You take 3 times 400 kcm equal 1200 kcm. Is this more than 1100? Is the largest 1100, right?
So you're like 10, 12%.
Is it's so if you're up to this, no problem. Then you go 1200 kcm. Is it larger than 1100 kcm? If the answer here is yes, which it is yes, then you take the 1200 kcm and multiply it by what? 12%, which is 0.125. One more time, the same calculation, guys, except if it's larger than 1200 kcm, 1100 kcm, then you have to do another step. What would that give you? What's 1200 kcm of Holly? What's it?
50?
150 even? 1200 times 0.125. 150. Awesome. 150 kcm. There's one little problem here. What is 150? Do they make 150? They don't make 150. So I need to convert the 150 into a language that we understand. Okay? One more time, guys. You do the same calculation. If it's larger than 1100 kcm, then you use the step. Brooks, if it was less than 1100 kcm or less, then you stay where you are. It will be 3 odd. Okay, because 150 is meaningless, I'm going to take the 150 kcm, guys. Chapter 9, which table? Anybody remember? Table 8. Chapter 9, table 8 can convert this to a language that we can understand. Is this 1 odd or 2 odd? Anybody can go check what's that one or larger. So you need that 150 or larger. Holly? So you need a 150,000 cm.
You do 1 odd.
1 odd?
Mhm.
3 odd?
Oh, 150. I'm being dyslexic. Yeah.
Okay.
That's right.
3 odd. Thank you. So that will give me, it stays the same thing, 3 odd. So it's going to be 3 odd. AWG cover. So this piece of equipment again, this piece of equipment is 3 odd. Did you guys go 150 or higher to get the 3 odd? Okay.
167.
Okay, perfect. So we're still 3 odd. We were right at, if you can see, we were right at the border. That's why 3 odd is good for us. Now here's my question for you. The neutral cannot be smaller than the grounding electrode conductor. What was the neutral? 4 odd.
4 odd.
Is the neutral smaller than the grounding electrode conductor?
Mm-hmm.
The neutral is smaller than the grounding electrode conductor. The neutral cannot be smaller than the grounding electrode conductor. But here's what the challenge though. The neutral is really bigger because we parallel though. Remember we parallel. The neutral in reality is 3 ohm. So we don't have a problem with that one because a neutral was parallel. Our neutral was parallel. So we don't have. Yeah, it was 4 odds. So in this case we're good to go. Any question guys about grounding and bonding? I can't emphasize. This is very important. When you finish sizing the neutral and the ground, you need to go the neutral and the phases. You need to size the ground, the grounding electrode conductor and the main bonding jumper. Main bonding jumper. Jumper P. Why did you guys tell me that it's a P, not B? P. Main bonding jumper. Any question, guys? And just to summarize, guys, what we've done, here's your 3 conduits. I always like to do that. 3 conduits that you came with. The 3 phases. And for these 3 conduits, you have conductor phase A, phase B, and phase C coming here. And you're going to have also phase B. This one is phase B, phase B, phase B. And the last one is I'm going to use black as, oops. Right here, Chad. Okay, phase C, phase C, and phase C. So I'm going to call this is A, this is B, and this is C. And guess what? With each one of them is coming what? A neutral. A neutral. Here's what paralleling means. I'm just throwing this one as a visual, guys. A neutral. This is my neutral. So this is basically what your system is. 3 sets of conductors. And the neutral was, what was it, 4-aught? 4-aught. And the phases, all the phases were 400 kcm. 400 kcm. So coming from the utility transformer here to the switch gear, parallel. What does parallel? They're color coded. All the blue will be tied at both ends. All the red and the black individually will be tied at both ends, and the green will be tied at both ends. That's what paralleling a switch gear is. To carry a 1000 amp panel. Any question is? Without making spaghetti, but you guys can use your imagination how these are going to be tied at the end together, and these are going to be tied at the end together, both ends, and the black are going to be tied at the ends together, and the neutral at the end will be tied together, and at both ends, from the transformer side and from the other side too. This is also, oops, there's my neutral, these together, and my black, here's my black, making a mess here, huh? And my phase, there you go, phase, and the last one is my neutral. My neutral. That's what paralleling is. You can see that all the phase A conductors are tied together, all phase B conductor tied together, all phase C conductor tied together, and the neutral conductors are tied together. That's what paralleling means. Any question, guys? So that's when we go to the commercial, that's what you're going to be doing. Paralleling conductors. Can you guys give me, I know it's lunchtime, but I started late. Can you give me just 10 minutes to size a lighting panel, and I'll let you go. Just 10 minutes, I promise. I want to size a lighting panel. We'll have all the loads are there. I just want to size a lighting panel and let you go. Promise. Any question about this? Yes, Mr. Webb?
No, I'm trying to see how you get to, when you get to out of concentration panels here, and you say go to chapter.
Yeah, go to chapter 9, table 8.
I cannot the collection of panels from here. So,
Mr. Webb, can I do it with you and later on after we go? Yeah, let me just move in that one because those guys get hungry and they get huffy on me and then we get in trouble here. I know people are hungry. Okay, I'm going to go back, guys, and size just the lighting panel, which really very easy. Go to this place, and I'm going to size the lighting panel, and I decide single-handedly for lighting panel to use red. Anything red is going to be lighting panel. So, Brooks, do you think lights, general lights, are going to be part of lighting panel? Duh, Chad. So this one is going to be, I'm going to put L next to them, okay? Do you guys think the receptacle should be in the lighting panel if I have a lighting panel? Why do you have a lighting panel if you will put the receptacle in it? Might as well call it general panel. So we're not going to put receptacles. Otherwise, why should we call it a lighting panel? So no receptacles. So this load, no. Signs are lights. So So it makes sense to have the sign, guys, on L. Okay. What else? Heat, cool. Bring it on. I'll put the heat and cool on lighting panel. That would be dumber than rock. Show window. Show window's light. So I'm going to put my lights for the show window on L, light. And track lights, that makes sense, Chad, right? Track lights is light. So I'm going to put it in light. Kitchen equipment, no. I'm going to put them in a different panel, on the receptacle panel. Most of the time, guys, kitchen equipment, receptacle panel. By the way, right here, you can size 3 types of panels. Lighting panel, receptacle panel, and mechanical equipment panel. That's what most of the time in the commercial building they have, guys. They have a receptacle panel, a lighting panel, and a mechanical equipment panel. You can do the rest, do it as a homework or as an exercise, not homework. But I'm going to do only the lighting panel. Only the lighting panel will size it. So I need somebody to pick these, highlight them so that you can give it to me, guys, later on. So I can size my lighting panel. Brad, Holly, you had them? Okay, I just want to write them down though. So if you guys have,
Yeah, I don't know.
you got them? Okay. So so I picked them all up. I'm going to go all the way to lighting panel, sizing, lighting panel. And the way it's going to go, guys, here's my 2000, my 1000 amp. Here's my 1200 amp. I took a cable here, and this will be my lighting panel. This will be my lighting panel. Main lugs only. Main lugs only. All these are my main panel. This is my main panel. I'm feeding them 1,000. Thank you. 1,000. Okay. So Holly, can you give me the numbers first? Number 1 and what the load?
General lighting, 219.
Light, that was 219. Okay. Next.
The sign is.
What was the sign for number for it?
What?
The number for it?
1.5.
No, the number.
Sign was
Oh.
3.
3, yep, 3, sign. Oops. I'm getting hungry. Sign and 1.5, right?
Mhm.
1.5K. Okay, what's the number?
Show windows number 6.
Number 6, what was that? Track light?
Show window,
Show window, and what was that?
10.
10K. And
Track
number?
lighting's number 7.
Number 7.
9K.
Track.
Yeah.
Track, and that was track lighting, and that was what?
9K.
9K. Anything else? Did we miss any? These are all the loads that can be fit for lighting panel. Who decided? I decided. There are lights. That's why I put them on lighting panel. What's the sum?
239.5.
239.5 kVA. Okay, piece of cake, guys. Then I will size the same thing. I will size first the panel for this one. I will call it, this is right here is number 1. The overcam protection device right here is number 2. Okay? Number 1 and number 2. And number 3 is the conductors. Number 3. Are you guys following with me? I'm sizing the overcam protection device, the conductors, and the panel. Let's do it. Go ahead and do it before you get mad at Chad here. I'm going to go number 1. Everybody knows what number 1 is. Number 1 is the panel. Panel size. Panel size. Piece of cake. We're going to go, I'm not going to go put codes or anything. 239.5 divided by 1.73 times 208. It's a 208 panel. What do you guys come up with?
667.
667. 667 amp. Okay, let's go size it from D wall. 667 amp. Take it to D wall. What was it? 3.13, I think, or 3.12 probably this one. Can I go? What's 800? It's an 800 amp panel.
Mm-hmm.
So it should be 13, right? So 3.13. That will be an 800 amp panel. Done. So my panel is 800 amp panel. Any question, guys? I have an 800 amp panel based on the calculation. Just the panel yet. We're not sizing the overcam protection device. I'm going to do with a different color, guys. Oops. I'm going to move this one here. Okay. Number 2, I'm going to do overcurrent protection device. overcome protection device, guys, 667 amps. You're going to take it to 240.6. What's the overcome protection device after that? 700? You have 700 amp. 700 amp. So I sized the over. So Brad, you're gonna go put a 700 amp right here. Yes, sir.
Does it say 26?
Which one?
240.
240.6. 240.6. 240.6. 667. Go with 700. Done. Last thing I want to do, guys. Any question about these? We size the panel. We size the overcome protection device. We're going to size the conductors. Now for conductors, here's what you can do. You can size based on the amps, like you said, Holly, because it's less than 800 amp. Engineering-wise, guys, get into the habit of always sizing based on the overcome protection device. Yes, you can size based on 667 amps. Please get into the habit of always size based in commercial industrial, in the habit of always sizing based on overcome protection device. So number three, conductors. Conductors, I'm going to say match overcurrent protection device, and please next to it CSK. This is Chad's way. Engineering wise, not code wise, you don't have to, you can go to the load. So here's a 700 amp divided by 2. I'm going to run 2 runs. 350 amp. Take this one to 310.15 B16. What would that 250? 500? 500. So give me a 500 kcm. 500 kcm. 500 kcm. All my lights. So my conductors will be then 2 sets of 3 conductor, 500 kcm, 3 conductor. And since it's lights and since it's harmonics, I know it's 800 amp and big. Since it's lights, since it's harmonic, I made a decision to pull a full neutral. I can't derate the neutral here. I make a decision to pull what? A full neutral. So that will be what? 2 sets, guys, of 4 conductors. Why 4? 3 phase and neutral. 2 sets of 4 conductors, 500 kcm each.
So you would put in the neutral for the lighting on
loads.
the main panel, but not
The
on
main
lighting
panel, I will completely derate. Lighting loads, guys, have harmonics in them, right? Harmonics
Yeah,
and
so
all
you
this good
can't
stuff.
derate them, but
Either.
you would in the main service.
I would in the main service.
Okay.
That's my way. I would in the main service. 2 sets, taking up one. Okay. All right, we'll see. Yeah, we'll see. Have a good one. The last thing is I want to just the grounding conductor done. I want to do the grounding conductor here. Brad, what you said about that here. Here's my grounding conductor, the ground. And I'm going to pull, and here's a ground here, guys, in the main, and here's a neutral. We bonded these together, remember? And we brought this to Mother Earth. I'm only interested right now in this conductor. See that conductor here? And that will be number 4. Everybody see that the grounding going from the main into the lining panel. Done. You size this one, Brad, based on overcome protection device. So my overcome protection device is number 3, or should be number 4. Why number 3 here? This should be number 4. Number 4. Ground equipment. It's called equipment grounding conductor. Technical term for it. Equipment grounding conductor, and or EGC. This is very easy, guys. You take the 700 amp and you take this one to table 250.122. And if you don't believe me, so you're going to go to article 250.122. It tells you to do the same thing. And that will get you what's the size cover. Always cover.
Wow.
Why not? So 1 out. Done. Done. Now, Brad, if you have a EMT conduit or rigid or intermediate, do you need this conductor? No. We don't need it. If it was an EMT conduit or rigid or intermediate, you don't need
The
it.
hospital, they need it.
Yes, we need redundancy in the ground. Yep. Hospitals, you need it in ground. Commercial building, no. Absolutely. Any question, guys? We're done. If you guys gonna go eat, sorry to take you away from your food. But any question? No? You can go eat. No problem. Any question, guys? Mr. Bab, what was your question, buddy?
Yeah.
When you finish that one, we can do it.
I have a question.
Yes.
And back here.
Okay, no problem. Let me just see if I'll be with you guys. Holly, does it make sense? No? Okay. Well, that will conclude that one. Okay.